Some months ago, we posted a video where we took a photographic camera gimbal like this one from DJI, attached one of our Lumix video cameras to it, and then co-mounted with the camera this powerful laser assembly, and then lined them up. Higher-end gimbals have an input that allows real-time video feed from the camera into the gimbal and a small processor so that you can designate a subject, like draw a square around my face, and the gimbal will keep me in the field of view. So if the photographer is moving around, the gimbal will keep me in the center of the field, or if you put the gimbal down on a table and I move around, the gimbal will keep me in the center of the field. And because the laser is co-aligned with the video camera, when the subject is in the center of your field, you can manually fire the laser and destroy the target. It worked, and it was actually a lot of fun. We really enjoyed it. And if you're interested, take a look back at that video. You'll see how we accomplished what we did. But there were a number of shortcomings to that system, and because we liked the process so much and we see the potential for this technology, we've decided to redo it and increase every single aspect of this system about 10 notches. This, though, required some technology skills that Alex and I do not possess. So I reached out for some help. I contacted an institution a little south of us, MIT. You've probably heard of it. Specifically, MITERS, MIT ERS or ERS. This is a student-run group that is hosted on the technology campus where they provide space, tooling, equipment, support, so that science and engineering students can pursue their own projects on the technology campus. It's a really neat system. I've had some contact with MITERS over the last few years, and I've always been very impressed, not only with the kind of projects that the students are doing, but also with just the philosophy of supporting this kind of independent research. It works very well. They put me in touch with Chris.
Hey guys, I'm Chris. I'm a graduate student at MIT and I'm studying robotics, and I'm super excited to be collaborating on this project with Tech Ingredients. All right, so I'm going to be spending a lot of time here in this video at the computer. I'm going to tell you guys a lot about the algorithms, the control, the machine learning that we use in this project, and how I'm remotely controlling the laser. But for now, we're going to leave it to Eric, and I'm just going to be pressing some buttons to fire the laser on and off.
And we're going to be covering both topics in this video. I think you're really going to like it. So grab your favorite beverage and let's get started. Now, in the original system, the lasers that we were using are probably more properly called laser assemblies because they consist of a large number of individual laser diodes, and all of them are co-aligned to produce a single beam. These diodes are pretty remarkable. They're based on the gallium nitride chemistry and typically are able to produce 6.5 watts at their maximum nominal rating. But I've worked with these things for over a decade, and I've found that they're very difficult to kill. As long as you can keep them cool, which we do by using these water cooling loops, you can push them past 8 watts each, no problem. Now, the way we have installed these diodes is as modules. These individual modules, there are 4 on this laser right here, have 20 diodes in each module, and they are manufactured by a company called Nichia out of Japan. And they manufacture modules from like 6 to about 28 individual diodes. And the reason they make these is that the blue beam that comes out of the module is focused down onto a glass disc that is coated with a phosphor. And the disc spins rapidly, like an old CD, to distribute the heat. But at the point of impact, it produces a brilliant white spot that is the light engine that drives the large projectors. The point of that is that because these are made for a global consumer market, they make a lot of them, and they are relatively inexpensive. You get a lot of watts per dollar. The laser that we used originally had 80 of these diodes and can produce over 600 watts of visible blue light, which is a lot. The new laser has 208 of these diodes and can produce over 1,600 watts of visible laser light. This is a remarkably high amount of power. I would wager that the majority of laser scientists, people who do this for a living, have never seen a laser beam this powerful. Typically, once you go over a kilowatt, lasers operate in the infrared. They're invisible. There are more powerful lasers than this in existence, but they're rare. And so what you're going to be seeing today, not a lot of people have seen. Before I dig into more of the details of the laser, I think it might be nice to show you what 1,600 watts can do to a target. So you can see we're getting serious. All right, the windows are blocked, the doors are locked, and we're going to be putting on our goggles, and I'm going to start running up the laser. All right, the powers have been set up, and the kill switch is still open. So Chris, are you ready? I'm going to engage the laser.
Yep, nothing should happen.
Okay, we're live. You have control, Chris.
All right.
Wait.
Stop.
Stop.
What?
Chris, can you record your screen? Are you recording it?
Oh, yeah, let me do that.
I just thought about that. That could be a useful
Okay.
thing to
All
have.
right, now I'm recording.
Okay.
Right, then everything's good then.
Okay. All right. So I'm ready to go. Power supplies are up. The kill switch is still open. I'm going to engage the kill switch. It's closed. You now have control, Chris.
All right, starting up the script. Putting the laser on the tire. All right, firing, 3, 2, 1.
All right.
All right,
Kill switch open. Man, it stinks in here. Cool that down so we can keep the fire department at bay. Cool. All right. So clearly, we've got the power. One of the banes of any kind of directed energy device is divergence, the spread of the beam with distance, which means less intensity at a distance. And at the fundamental level, it is unavoidable. It is a principle of electromagnetic radiation, light. Whether it's radio waves, light, or X-rays, all electromagnetic radiation will diverge. It's an expanding spherical wavefront. You can't prevent it. However, you can minimize it. The problem is, we're using a kind of laser that adds additional divergence. It gets worse. And it's based on the way that lasers work. They're actually relatively simple devices. In a laser, you have a gain medium, something that will glow or release light when energized, either with electricity or another light source or even chemically. The light that is given off by the gain medium, though, is distributed omnidirectionally, isotropically. It's the same in all directions. However, a very, very small fraction of that light that's released by the gain medium happens to be traveling right out the end of the gain. And if you position a mirror at that location, you can reflect that particular ray path back into the medium. As those photons travel through the medium, they interact with the atoms that are being excited, that are producing the light. And if one of those photons gets close enough to one of those atoms, it can induce or stimulate that atom to release its photon at that instant and in the same direction as the photon that stimulated it. Now you've got 2. And as the ray is moving through the material, they may encounter another atom. Now you've got 3. Eventually, that ray gets to the other side of the laser where you locate another mirror and send it back for another pass, and then another pass, and another pass. Unlike any of the other ray paths through here, that particular path gets to spend a heck of a lot more time in the gain medium, building up energy, adding photons to the laser beam. And as a result, it sucks all of the energy out of the system, all the oxygen out of the room, so to speak. And this continues to build up intensity along that particular pathway. If you design this where one of the mirrors is a little bit leaky, a little bit less than 100% reflective, you can tap out a small amount of that energy in the form of a laser beam. That's how they work. And it's very effective. However, diode lasers suffer from a geometric challenge because in a typical lab laser like this, these mirrors may be located a meter apart, and so you have to exquisitely align those mirrors so that they're facing each other and keep the beam traveling back and forth between the mirrors. That means that the beam that comes out is very well collimated and has a minimal amount of divergence. The diode laser, however, is built in a different fashion. The mirrors can be microns apart and have a relatively large dimension in the XY. So as a result, even though the process is identical, what can happen is some of that reflection is going to be going back and forth directly like we had before. But there can be ray paths that do a little bit of a wonky sort of zigzag as they're working their way out from the edge of the mirrors. They spend enough time inside of this material to generate some laser output themselves. The result is that the divergence from a diode laser is not so fine that you can't even see it as you can here with a typical lab laser. The divergence from a diode laser can literally be this big. It's huge. And that's why on the front of these diodes, when they come from the manufacturer, have this sort of waffle pattern of little bubbles. These are actually corrective lenses that help to reduce that divergence and tighten up the beam. They do a very good job, but there's still a little bit of additional residual divergence based on that property because of the way the diodes work. For us, the problem gets even worse. Because the individual diodes are mechanically mounted into these modules, and then I mechanically mounted the modules into the laser, those individual laser beams can be misaligned, sort of like a bundle of sticks, adding additional divergence to the overall output from the laser. Now you may think, well then why did you use this laser? Why not just use, say, a fiber laser? It'd be an excellent choice for this. And you'd be right, it would be. The reason we did this was because, number one, as I said in the beginning, you get a lot of watts per dollar out of these diodes. They're also modular, so if you're doing a project where you want to use, say, 1 diode or 4 or 8, you can mix and match them for other projects. You don't waste them because they're very flexible. It's a nice tool. What makes this, though, possible is that there is a way to reduce that divergence almost without limit using a very simple technique. It's called a beam expanding telescope. Effectively, what happens is the amount of divergence that comes out of the system is related to the diameter of the beam as it exits the system. If you double the size of the beam coming out of the laser, you will cut the divergence from all of those sources in half. If you increase the diameter of the beam tenfold, you'll reduce the divergence tenfold. It's almost limitless. It's just a matter of how much room you've got available. The way you do that is by using a telescope that only involves 2 lenses. You might think, this seems kind of crazy because we want the highest intensity at a distance, and you're telling me that in order to achieve that, I'm actually going to make the beam bigger at the source. It works because the narrower diameter beam that's diverging will eventually catch up with the larger diameter beam that has a lower divergence, and eventually at this point and beyond, the unexpanded non-telescopic beam will be less intense at the source. The 2 types of beam expanders or telescopic expanders that are often used are the Galilean and the Keplerian design. We're using the Galilean design, and that is this one up here. Just two lenses. A concave lens that expands the beam in a controlled fashion, and when you get to whatever magnification you want to achieve, you place a second converging lens that recollimates the beam into as close to a perfectly columnar beam as possible. The other method is called the Keplerian design, still just two lenses. But the first lens is actually a converging lens. So the beam reaches a focus at this intermediate point, then expands and once again is recollimated by a positive lens. The upside of this type of design is that because of the narrow focus at a short distance inside of the telescope, if you have a low-powered laser and you want to clean up the beam, you can pass it through a pinhole at this point, which blocks all the spurious light that might be coming from your laser generator, and you produce a very clean beam in the distance. The downside is that this is obviously a bulkier system. It's longer and heavier. And the focus that's reached at this point, if you're dealing with very high-powered lasers or pulsed lasers, can achieve an intensity that can actually tear electrons off of air molecules and form a plasma inside of the telescope. And this will completely mess up not only your telescope, but your optical system, and so you don't want to use this with very, very high energy lasers. The telescope that we're using here is a 3-power scope that's mounted in front of each one of the individual modules. So we have 8 telescopes here. By concentrating the light at a distance 3-fold by 3-fold, we increase the intensity 9 times compared to the non-expanded beam. But it's even better than that. If you look at the front of each one of these telescopes, I have these small threaded rods with springs that allow us to fine-tune the spacing between the lenses to get everything focused right. But you can also tip and tilt this second lens to counter some aberrations that may be present from the underlying laser module. So 9-fold concentration increase is a bare minimum. It's closer to 14 in this laser. So by using 2.5 times as much power, we're actually reaching intensity levels at a distance that's close to about 30 times as high as the laser that we first demonstrated. I'm going to show you what that kind of concentration can do. Now we've got 2 test targets here. This is an aluminum oxide fire brick. It's made for high temperature furnaces and kilns. And aluminum oxide has a melting point of 3,700 degrees Fahrenheit or 2,100 degrees Celsius. I'm going to block this in here in the vise. And then we're also going to use a piece of stainless steel sheet. I'm going to put this over here. And even though these objects are highly reflective, it isn't going to save them. All right, doors are locked. Everybody got their goggles on?
Yep.
Okay, Chris, I'm going to close the kill switch on 3 and hand the control over to you. 1, 2, 3. Okay, laser is live.
All right. We're going to move over to the fire brick. Right around there. All right. Firing in 3, 2, 1.
Now the white glow that you can see is not the laser. It's the fact that the fire brick surface is white hot.
All right. That was about 45 seconds.
All right.
Turn the laser off. And moving to the stainless steel. All right. Firing 3, 2, 1.
Yeah, I think you're pretty good.
All right.
All
Laser off.
Kill switch is open. Let's go take a look at what we did. Oh, wow.
And
Yeah.
you know what, Doc? I'm going to take the camera down here, and I'm going to follow you over there.
Okay. That's probably better because these are hot. You can see this is sort of the beam shape right here. And you can see that we've actually melted the ceramic and formed aluminum oxide glass, which is the same formula as sapphire. We formed sapphire glass. And this is obviously the hole in the stainless steel that the laser is currently shining right through right now. There's some heat damage that's done by the laser, but the spot is better indicated on the ceramic block. So you can tell we've got the power and we've got the intensity for our project. I was ready to hand this laser over to Chris so that he could begin implementing the control system. And we began doing some simple tests and we discovered a problem, a big problem, and it was totally my fault. You see, one of the reasons why I think Dr. Nakamura was awarded the 2014 Nobel Prize in Physics for the development of the gallium nitride laser chemistry was because of the global significance of that invention. You see, if you remove the mirrors from these diode lasers and you just use the gallium nitride, it is an extremely efficient emitter of bright blue light. And if you place a phosphor on top of the diode, like this phosphor, it's called YAG, yttrium aluminum garnet, and it has a yellowish powdery appearance. This material fluoresces brilliantly under UV and under blue light. You can see it here in the beaker, and you can see it here where we've made a coating for a future video. And so what they discovered they could do is by placing a thin layer of this material on the blue diode and allowing some of the blue light to leak through, the combination of the blue and the yellow appear to our eyes to be white light, and it is illuminating the planet. If you're watching this video with lights on in the room, there's a very good chance that you're actually benefiting from this principle right now. Next time you take a look at your LED flashlight or the emitters in your LED bulbs, take a close look and you'll notice they have a slightly yellowish tinge. It's from the phosphor powder that they put on the top of them. The problem, though, was that there are not just a few rare materials that will do this. There are thousands of different types of compounds that, under the influence of the blue light, will fluoresce. For example, this is a dye called rhodamine, and it's typical of a number of dyes that are used in plastics, in clothing, paints, toys, and when illuminated by the blue light, fluoresces brilliantly orange. It's pretty. This is honey. See the bluish cyan color?
Yep.
This is olive oil. It also fluoresces, slightly bluer version than the honey, but clearly it fluoresces. This is vitamin B12, or riboflavin. And if you put a couple of drops in some water, 3 drops, stir it around a little bit, it fluoresces, more of a cyan or a green color. This is a green pepper. The blue light can't easily get through the skin, but if you slice it like that, you can see that it fluoresces reddish. They call it a green pepper, but not under blue light. And some of you are probably getting an idea of what the problem is. Because there are so many compounds that can fluoresce, and because they can fluoresce at various wavelengths, we've got an issue. Because the intensity of the light that's given off by the laser is so great, the fluorescence is blinding and actually can wash out the camera. You can't see what you're trying to track and target. Now, you notice that we're wearing these protective goggles, and they are very good at blocking the specific wavelength of the laser. They block the blue beam and allow all the rest of the room light through so we can see what we're doing. The camera itself also needs a goggle or filter that protects the light-sensitive chip in the camera from damage due to the intense radiation given off by the laser. The problem is this fluorescence can occur at unknown frequencies and unknown wavelengths, not in the blocking range of the filter. Now, it turns out that the solution to this problem in retrospect was actually pretty simple. It's due to the inefficiency of the fluorescence process. There's a thermodynamic law that says if you hit something with a photon of a certain amount of energy, you're not going to get a photon given off by the product at the same wavelength. There's going to be some energy loss. In other words, there's going to be some red shifting to the fluorescence. You'll notice that all of these compounds, when they fluoresce, even though they fluoresce at slightly different colors, they're always to the red end of where the laser is operating. So what we did is we replaced the bandpass filter that we were originally using with what's called a short pass filter. It blocks everything from slightly blue of the laser output all the way through the visible and into the infrared, so we no longer blind the camera. But that presented another problem. We're now visualizing, or we're now imaging through a very small amount of light that's let through into the camera. So we had to modify the camera system. Originally, Chris was kind enough to donate one of these Basler machine vision cameras to this project. The problem was it was a color camera, and it has RGB filters in front of each one of the pixels, and so as a result cuts down some of the light transmission and reduces its sensitivity in the blue part of the spectrum where we're going to be imaging substantially. So we got a replacement camera that has a monochrome chip and substantially increases the amount of blue sensitivity, and that wouldn't be a problem for us if we were imaging outside, because the sun produces a great deal of blue, deep blue light. But because of the power of this laser, we're compelled to work inside for safety. And so in addition to the more sensitive camera, we had to add some additional lighting because we're located inside. This did work well. And now we're able to hand this operation over to Chris so we can actually turn this in to a functional laser-directed laser device.
So you guys have heard a lot about blue lasers, collimating lenses, and fluorescence, and a little bit about how we're going to use this camera to take images of targets downrange in order for us to point the laser at them. But I want to spend this time to talk a little bit more about our hardware setup and how we've got this set up to actually do well at tracking targets. Now, at a high level, you can see we have our 8 laser modules here aligned with our camera, whose job it is to take images of the targets downrange. And we can move this assembly with this gimbal here, powered by these 2 stepper motors. This allows you to get yaw and pitch to allow us to point the laser at any target within the field of view of the laser. These stepper motors are driven by these 2 stepper motor drivers here, which by themselves are pretty dumb. They receive their signals from the motion control board. The motion control board receives the signals that we want to be sent to the motors, for example, velocity or position, through this USB cable back to the main computer. So if you can envision the loop here, we take images of the targets with the camera. Those images go to the computer where they get processed. We make the decisions of what signals to send to the motors, which come back through the USB cable to the motion control board. The motion control board translates those commands into pulses to be sent to the stepper motor drivers to drive the stepper motors. Now, I want to talk a little bit more about this camera because it's special. This camera is from Basler, and they make really excellent cameras and really expensive. And that's because they give you a lot of fine control over all the parameters of the image that you're taking. For example, the exposure time, what part of the sensor die you're actually using, and all these factors allow you to change the FPS, or how fast you can receive images from the camera. This camera is used a lot in machine vision projects, and it's very popular because it's really good at what it does, and that's why we selected it for this project. Now, talking a little bit more about our motors and how we chose them. Stepper motors are kind of an obvious choice for this project because they allow you to get really fine precision position control, velocity control, acceleration control, and limits on all those variables. And they're quite cheap, and they're quite easy to drive as well because they can be driven by very cheap electronics such as the Teensy 3.2. The Teensy 3.2 is the heart of the motion control board, and the Teensy is really a step above a lot of the other Arduino microcontrollers you might be playing with because of its really high clock frequency. That allows us to generate really smooth and good motion control signals to be sent back to the stepper motors to allow us to get that really fine and high frequency control. Speaking about high frequency, the targets we're trying to track might be moving around really quickly. And that's a problem when you have to accelerate this really large mass of a laser. It's quite big. And so to achieve that, we need a lot of torque, or a lot of force, to move that inertia, which is why we have a pulley belt reduction here from the stepper motors. You can see we have a small pulley here at the output of the motor, which drives this big pulley here at the base of the laser. And that also exists here on the x-axis to change yaw. And it makes sense why you might want more torque, which naturally comes from a larger gear reduction, but there's another effect at play here, which is the fact that for one rotation of the stepper motor, a large gear reduction will cause a smaller change in angle of the gimbal. When you combine those two effects, the apparent inertia of this gimbal, which remember, inertia is the thing we really care about, the apparent inertia of the gimbal from the perspective of the motor is decreased by a factor of the gear ratio squared. So getting rid of a couple of teeth on the driving pulley really helps. We got it down to basically the smallest you can get away with before the belt skips. And that allowed us to get the highest accelerations of this large mass to allow us to track fast-moving targets. Now, we understand a little bit more about the hardware, but I want to talk in more depth about the loop, or about how we take images from the camera, process them, and produce those corrective signals so that we can track targets that move quite fast. So I've talked a little bit about our hardware setup and about how we've set up the system to actually track targets, but I actually want to demonstrate to you us using this laser with this feedback loop to actually track targets on the scene. So you can see here, we have an RC car here, and the laser pointer is showing us where the laser would be pointing if it were turned on. And you can see it's not omnipotent, but it's staying on the car pretty well. And if you consider the fact that we are accelerating this heavy mass, and we do have acceleration limits in this system, we're doing pretty good, much better than a human could. And also what a DJI gimbal could do out of the box. Now, I can assure you that this kind of tracking is not magic. There's a method to this madness, and I'll explain it to you with a system diagram of the system and how information is flowing from the camera to the computer and producing the corrective signals needed such that we actually can track the cars and the targets. Here you can see an overview of the system in block diagram form. And I'll explain it to you step by step. And we'll start up here with the environment. In this box, you can think of this representing the actual world, the physical environment, where we have things like cars and we have things like lasers with gimbals with cameras. Now, what are we ultimately trying to do here? Well, the laser is set up to be pointing at some position. The angles of the gimbal are some value, and we have a target that we'd like to point the laser at. So you can see here the target position, and we're comparing this here to where the laser is pointing. We want to make corrective commands to the motors such that we move the laser position to the target. And that starts with taking an image of the scene, measuring the system. We have the Basler camera up here, and that Basler camera produces images which get fed here to the computer. And I'll explain how the computer processes the images to produce those corrective signals. First, we feed that image to an object detector. And for now, we're going to take for granted that the object detector is capable of taking an image and giving us detections. basically where objects of interest are in the frame. Once we know which targets are where in the camera's frame, we need to make some decisions about which targets we want to track, and also keeping track of, if there's potentially multiple targets, which target is which in between frames. We've implemented such an algorithm. Now, once we have the target position, the single target we'd like to point the laser at, represented here with the red X, like this car, we compare it to where the laser currently is, which is represented by this blue dot. And remember, the laser position being mounted rigidly with the camera is always in the same spot in the camera's field of view. So we can hard code this position. It always comes with the camera. We have a controller here, which we'll go into more depth in just a moment, which takes these two reference signals, sees their difference, and intelligently makes corrective commands in the form of motor velocities. These motor velocities then go to the motion control board here, the Teensy 3.2, which translates it to the motor drivers. And the motor drivers do the heavy lifting to actually move the motors. And in a single loop of this control loop, we'll move the laser position marginally closer to the target position. This whole loop, in the case of this laser, runs at 60 times per second, approximately. And the more the merrier. The higher your refresh rate, the more aggressively you can tune your controller to make the laser position reach the target position. Now, what is this controller? It kind of looks like a black box, and it is, but I'll explain the controller we're using in this project. Here's an example of our controller, and you can clearly see we feed in the target position and the laser position. And you can see in the controller, it takes the difference between the target position, where the object in the image actually is, and the laser position, where the laser is currently pointing, always the center of the screen. When you subtract those two quantities, you get the error, or you can think of it as a two-dimensional vector in the camera's space, x, y. That error represents the distance that you need to travel to be on target. Now, what do we do with that error? Well, in the case of this project, we used a PI controller. Now, you might have heard of PID control and a little bit from control theory, but without going into too much depth, because there are entire textbooks written on the topic of control theory. There are entire YouTube channels dedicated to it. People have made careers out of understanding this. I'll explain in very simple terms how the PI controller works. In this case, you have an error which points in the direction you want the laser to move, and we do two things to that error. We first multiply it by a constant, Kp, basically telling the motors to move in a velocity proportional to the error. So basically, if I have to go up and to the right, I move with a velocity proportional to that error. Seems simple enough. Why would you need anything else? Well, consider the case where a car is moving, and because there must be an error for you to move with the car, you'll always kind of lag behind. That's why we introduced the integral term, the I term, which is this path down here, where we take the error and we integrate it over time. Basically, if there is steady state error, meaning error that persists with time, the integrator will build up in value. That value we then multiply by another gain, Ki, which is a number I play around with as the programmer to get the system to respond well and quickly and not be unstable. And we take the result of both of these paths and sum them to produce our motor velocity. This is the signal that gets sent to the motion control board, which closes the loop. Now let me explain what I consider to be the heart of this project, which traditionally has not been possible to do, and that's YOLO. YOLO is an object detection network that can take an image of objects that the camera might see on this laser and produce detections, or these rectangles that show us what and where those objects are in the image. YOLO is very special because it's much better than what came before it. YOLO, which in our case, we're using YOLO V8, is capable of making these detections on an image at 40 to 155 times per second. That is absolutely insane. Comparing that to previous methods like fast RCNN, the basic method that they used would be to take the image and then slide this window over the image, basically extracting a sub-image, passing that to a classifier which told you what class do I think this is and how confident am I in that answer. And the classifier in and of itself is quite fast, but you had to slide this window all around the image. You'd need about 100 to 1,000 of these sub-images to really get a good idea of what's actually in the image. YOLO completely breaks this idea by taking the image and just feeding it straight through, giving you the answer in one pass. Although YOLO in and of itself might be a little bit more complex than whatever classifier you might be using, the fact that it just goes straight down, I mean, that's why it's called YOLO, you only look once, is why it's so fast. Now, how does YOLO work, and how do we differentiate between what objects we want it to detect and what we don't? Well, we have to ask ourselves how we train YOLO. Like with any machine learning project, you need data, right? And here you can see we're going to supply YOLO with a collage of images that we have hand labeled. Basically, we take a bunch of images of RC cars driving around, of drones flying, and we save those images. And then me, manually, will draw rectangles around the objects and tell YOLO what class belongs to that rectangle. So for example, cars can be denoted as red, and drones as blue, and people as purple. And for any other objects you don't want to detect, you simply don't draw any rectangle. YOLO will learn not to get confused by them. And so you can see here the class list that YOLO is able to predict is finite and chosen ahead of time by the labeler. We take these images and their labels and we pass it to a Python file like train.py. This comes from the open source repository that is maintained by Ultralytics, which you don't really have to do any coding. You kind of just pass these images to this file that they've already written for you. And in the case of this project, training this on my GPU, which is an RTX 3070, this process can take anywhere between 1 and 10 hours. Fairly fast. And the result of training is a file, which you can name anything, but in this case, custommodel.pt. It's about 50 megabytes in the case of using the medium-sized network, and that's it. With this file, you can do those forward pass detections, and you can distribute this file to anyone you want, and that completely encapsulates all the learning, all the complexity of YOLO, of the network, the underlying network, that allows you to make those detections. And so you only have to do this process once. Although it is painful to label all these images, and it may take 1 to 10 hours to produce this file, once you have it, you can make fast, reliable detections. I explained previously that YOLO can produce these bounding boxes, these rectangles, that are laid over the image that show us where objects are on the screen. But that in and of itself is not enough for us to know which car is which through time. For example, if you have multiple targets, we might want to know which target is which. If we assign them a name or a unique ID at some point in time, we want them to carry that unique ID or name into the future. So I'll demo this system. I'm going to start my script, and right now the laser gimbal will not move, but we'll be able to see what the camera sees. So right now you can see it's just a blank background. We're going to drive one RC car into view, and once that RC car is into view, you'll see here on the screen that we are now tracking it. Tracking is a little bit more than just detecting it, because we've assigned that car an ID of 0. Every time a new object enters the frame or enters the view of the laser system, it will be assigned a new unique ID. So for example, if we have a second RC car come down the ramp and into view of the system, you'll see here on my screen that this RC car now has an ID of 1. So 1 greater than 0. And it'll keep these IDs persistent through time. Consider the case now if one of the RC cars drives behind the barrier and can no longer be seen by the system. You can see that the RC car has now been lost, and if that same RC car drives back into view, it will now be assigned to ID 2. The system assumes ID 0 is gone, and of course our system cannot track the car that it cannot see. So instead, when a new car enters frame, it assigns it the next unique ID, which is 2. And this unique ID persists through time.
All right, the power supplies are at 70% power, and I'm enabling the safety switch on 3. 1, 2, 3. All right, you've got complete control, Chris.
All right, in this experiment, we're going to fire upon the balloons in left to right order so we can see how fast the system can track the next target. I'm going to start the script, and it's going to point at the leftmost balloon. And when I hit the space bar, it's going to start firing. All right, ready? 3, 2, 1. All right, stop. All right, stopping.
Safety switch open. Excellent.
Nice.
That's cool.
All right, clean up in aisle 1.
The least favorite time. Okay. All right, ready to do it for real this time? In front of
Well,
you?
that was real.
Sorry, I meant
The
the
danger
danger
zone.
to be real this time. That's what I meant to say. Yeah,
Yeah, it's like, I think that's pretty real.
that was real. That
Seemed
was like
real to
30
me.
minutes of effort. It took
Remember,
like a
screen record.
fuck.
All right, this test is going to be pretty intense. You'll see why. I'm enabling the laser on 3. Everybody got their goggles on?
Yep.
Yep.
Okay, here we go. Laser's live. You have the control, Chris.
All right. What's going to happen in this experiment is very similar to the previous, but we're also going to demonstrate the ability for the system to disable if a human is detected downrange. Now, Eric has volunteered himself to get in front of the laser and trust my code with his eyes and with his clothes not being on fire. But what should happen is the laser will refuse to fire until Eric himself disappears behind the barrier. Then the system will proceed as normal, and we might see some other balloons before the test ends. All right, the laser's been enabled. I'm going to start the tracking script, and the laser's going to point at the leftmost balloon and travel left to right. Okay, now that the script's been started, Eric, you can walk up.
Okay.
Good luck.
Thanks a lot, guys.
Okay. All right, I can confirm that the computer sees you, and when I hit the space bar, nothing should happen. Laser is being fired if you disappear, so do your thing.
This is trust.
All right, I'm going to disable the system. Give me a second. All right, I've hit the safety switch. You can come out.
Okay.
All right.
Congratulations.
Okay,
I'm alive.
let's go. It actually worked.
Very good.
Good job.
Whoa.
Hell out there.
No legal trouble. Okay.
All right. I need a drink.
So you guys saw the capabilities of this system in the previous experiment where we were able to track targets through time and remember their unique ID so that we knew which target was which. We're going to do something very similar in this experiment where we're going to be tracking RC cars, except for the fact that RC cars are a little bit different from balloons and cats in that they take a little bit longer to burn under the laser's fire. So instead, what we're going to do is have the laser autonomously dwell on the target for a fixed amount of time before proceeding autonomously to the next target. When it reaches the last target, it'll cycle back to the first target in a round-robin fashion. If any of the targets are obscured or go missing, it'll just skip it and go to the next one on the list. All right.
All right. I'm going to enable the laser on 3. 1, 2, 3. You have control, Chris.
All right, starting up the script. It's going to point at a car, but it won't do anything until I hit the space bar.
All right.
All right, starting the experiment in 3, 2, 1.
I can't not laugh at this. Like, it's
Yeah.
awesome.
Looks like it skipped me. I must have been undetected. But it
No,
should,
I'm trying to go
no, I'm
straight.
just saying about what it's doing.
Yeah.
But it should be round robining pretty well. Oh, look at that. We all got mixed up. So it confused one of us with another, but we'll see. Oh my God,
Okay, I can't.
he's on fire.
Keep going.
We got time. Come back into frame. Come my God, the smoke is such a cool effect.
You guys are running into me. Stop.
Oh man, you're really on fire.
Yeah, we might have to deal with this in a second.
We're having too much fun.
I'm trying to get away, but
Oh, don't go into the foam.
no, but I can't help it. We gotta stop. I can't turn.
Okay, that's fine. We can keep going.
Car is damaged.
We can keep going.
I
Even-
can't
Then just
turn.
stop it.
That's fine. You want to stop it? I mean, we can keep going. It's,
No, I mean just stop your car and let it burn.
yeah. Oh man,
The other one's
you can't turn anymore. Here, let me get you out of frame. Oh, he wants to kill you.
Yeah. Okay. Well, I can. No.
Oh, it thinks
I
I'm.
can't do
It
anything.
thinks I'm you now.
actually Anymore. Yeah, it is dead. My car is dead.
All right, let the experiment continue.
Yep. Oh,
Oh, now I'm on
we're
fire.
getting there. Yep.
This is such good footage. Just let it happen.
Yeah. Burn the thing more. Yeah. There we go. That's better.
I can't turn anymore.
Okay, I can bump you.
Yeah. Until you burn.
It's got me. No.
You burn. You burn with us.
It really. Oh, I'm stuck on you. Oh no.
Really? They're all up.
Okay, I think we gotta
Yeah,
stop.
but-
All right,
you-
disabling.
please,
Turned off.
please. Before the fire alarms go off. Yeah.
Okay. Oh my God, I was.
Much fun to be legal. This thing is a molten pile of plastic and I don't know what.
Yeah, it was. Yeah, it was burning for about 2 minutes. Yeah, I would assume.
Oh, no, oh, you don't want to see. Oh.
Let me see what's up.
It's,
You said it wouldn't turn in. Oh my
it
God.
did turn into a puddle.
It
took off the-
No, don't fuck with
It took off the first two. Jeez.
Look at it. That's ridiculous. It's like pudding.
What were you saying, Chris, about it's not enough time to destroy them?
Well, if you dwell on it for like a whole
It
minute.
melted them.
Ooh.
Yeah, don't.
Oh.
Bad idea. Bad.
Stop doing it.
Look at that. I kind of want.
Medieval times.
Oh
when they
my
dripped
God.
Oil on
Oh,
you.
there's the battery. Oh,
Oh,
that,
good, the battery.
it's still there.
Yeah, can we make sure after we're done with this,
Hold on a second.
keep the batteries outside?
I just want to cool these things down a little.
Sure. But after this, we have to make sure to keep these batteries outside.
I think
Because
before.
it'll burn down the.
Yeah, and also just the top of the stuff. I think what we need to do is we're going to need to clean this stuff up because anything else that happens here, we're going to be stepping in.
Yeah, right.
So,
Right.
I also have bad news. I was not screen recording. That was the one time.
You fucker.
well, you know
No,
what?
it's
We
fine.
got other
No,
footage.
it's
Yeah.
fine.
It's fine.
So as you can see with that last experiment, we programmed the system to visit each car in a round robin fashion, basically proceeding to the next target kind of like in a loop and do that consistently. Something we didn't foresee with this experiment was potentially two things thwarting us, which was the fact that the very intense flames from the RC cars were not things we trained YOLO with. When we collected our training footage, we did have some fires because we knew we would see them in the final implementation, but we didn't necessarily show YOLO how intense flames can get. So it might have been a little bit confused by the flames. And as well as the fact that we were really driving the cars on top of each other, you can consider this potentially a limitation of YOLO, but if you have two RC cars like right on top of each other, YOLO might return a single detection that kind of represents both RC cars. And the tracking algorithm really has no chance to be able to differentiate those two cars or track them through time. So in that case, when they're right on top of each other and split up afterwards, the tracking algorithm chooses to assign one of the cars a new unique ID. And in that case, we're not kind of doing round robin because the IDs are changing constantly. We're not really going to go in that predefined pattern. But we definitely did do some good destruction, and the round robin pattern definitely spread the laser fairly evenly across all the RC cars. So I would still consider the experiment a pretty good success.
All right, we've come to the final demonstration. As we indicated in the thumbnail, we are going to be taking drones out of flight using this laser. And all of the systems that we have demonstrated and all of the control algorithms that we have explained were designed to build toward this final test. So we're going to take off with a couple of drones and we're going to see what this laser is actually able to do in a real-life situation against drones. I think you're going to like this. Okay, Chris, you now have control.
All right, starting up the script. The laser will point at a drone, but not fire until I hit the space bar. All right, everyone take off. All right, starting firing. 3, 2, 1.
Well, that one's dead.
Whoa, that's the battery.
Yeah.
Oh,
And it ignored it.
Oh, and this is, it's really,
it's good. It's okay. It's good. It's good. It's good. Can't spread.
I'm trying to keep it normal, but
There's your battery. It's going.
yeah.
Oh, we thought it would. Okay.
It thought it died.
It thought for a second.
Boy, your drone
I'm
is
the
really
last
Go
one.
robust.
forward. Go further. Go forward. 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 You can see where the laser converges. Oh man, that
Yeah.
that battery's going off.
Yeah, but
Alex, go forward.
I'm trying.
Oh, it's coming back. You mean? Like,
Yeah, it's doing
It's going
that by
crazy,
itself.
okay.
Like, and I'm.
You have like no control anymore.
It's. No. Oh my god.
Meanwhile, it's lithium-ion battery fire.
Right.
Yeah, right. It's burning and it's
Why did mine only last 4 seconds lose
I
control?
think you must have hit something. Oh,
I couldn't control
You're
it. I
boned.
lost control.
You're boned.
yeah.
Okay, disable it.
Multiple fires in the Middle East. Yeah, Kimmy.
It might not go out. It might catch back on fire.
Where'd the third one go? Because I wasn't paying
This one up
attention.
here.
Oh, okay.
Oh, one of the propellers broke.
Oh,
That's why it went down so fast. Okay.
Yeah, it was like I just lost control and it was like boom. It knocked one of the propellers right off of it. That's accurate.
And that smell is.
Oh, that's
Awful.
delicious.
oh, that's the battery. Actually, we shouldn't be
Yeah.
smelling this.
Can I open the?
Yeah, I'm gonna get the shower.
Oh boy, that's the battery,
Yep.
and you're dead. It's going crazy. I can't really control it. It's getting harder. And I'm kind of falling. I'm really losing control. It's kind of going crazy. Oh, there's the battery.
All
Okay,
right.
disabling.
All right. Safety switch
We got
off.
2 battery fires. Oh, it tried to take off again. Oh my God. What the heck is that?
But the last few joules in the battery.
This thing's a tank.
Yeah.
Oh, it's kind of acting a little weird. I feel it. Oh, it's kind of losing power. Ooh, that's the battery.
Flame in flight.
It's trying to
Disable.
It's dead. Okay. Put the fire out. All right.
Whoa. That.
Good job.
Oh my God, it looks like you just basically cooked the entire structure away from the battery. You see, it's like the whole top has been burned.
The battery's just sticking out.
Yeah. The battery's the only part that survived until finally.
All the plastic melted around.
Yeah.
That's crazy. It did puff. I mean,
Yeah.
the battery clearly didn't survive, but
Yeah, you could tell by the red
it's the only
flame.
thing that's really sticking out.
Yeah,
That's crazy.
yeah.
And if you want, I can look at that,
Yeah.
but I get a good view of it happening.
All right,
Yeah, it's not really smoking right now. I think I can just hold it here for a
guys. No, I'm joking. I'm joking. I'm joking.
Yeah, at this point,
I think we need a human target.
I mean,
Let's see how fast Chris can run.
It's not that hard to change what it shoots. That's all I'm saying. That's all I'm saying.
But he never told us how to target humans.
well, you don't need to. Do
He's
it
a bit of a
manually.
pacifist.
Well, no, do it manually.
Yeah, right.
So you can see here the laser ate everything except the battery, even though we did have a battery fire. It seems like the battery is the most temperature resilient.
Yeah, and you can
thing
see the
in there.
PCB board is exposed here, and
Yeah.
actually some of the drone arms, like this one, looks like it's almost melted
A little
off.
bit soft.
Yeah, see this
Right.
one here?
Must
at
have
the
hardened
root?
up, but
Yeah, right.
Yeah.
that's crazy.
Well, this video was a real blast. I think we had more fun doing this video than any that we have produced to date. And it's been a real pleasure working with Chris. He is talented, has a great sense of humor, and I learned a lot in the time that we've spent developing this project. And in keeping with that, if you are a researcher or a company that is interested in the kind of technology that we demonstrated here, we've put a link to Chris's website below the video if anybody wants to contact him and have further discussions about this. Now, some of you out there, as much as I suspect you enjoyed the video, may be a little bit troubled by the subject matter, maybe even a little concerned. And we share that concern. It's not the high voltages that we're dealing with, or the very high-powered laser, or the inhumanly fast control system. Lasers are becoming progressively more powerful, more robust, more compact, and cheaper. And despite the fact that I'm pretty well versed in this area of technology, I have trouble keeping up with the progress in laser technology. Computers are becoming faster, and the control systems and software, the algorithms that are controlling them, are also progressing rapidly. Nevertheless, despite current technology, you've seen what we were able to produce, 3 guys in a warehouse with a minimal budget. You can imagine what might be done if you had 10 researchers and a budget of a couple of $1 million. It's frightening. And the reason that we were motivated to do this video is because we wanted to demonstrate that this kind of technology is currently being used all over the world, and it potentially represents a threat that many of us may face in the future, and I think it's something that we have to keep in the back of our minds. Nevertheless, I don't want to leave you black-pilled here, because the same technology that we've used here to produce these destructive lasers can also be used to save lives. There are new lasers that have recently become commercially available. They're called quantum cascade lasers and frequency comb lasers. These are very interesting. They're low-powered lasers, some of which are even eye-safe. You can expose your face and your eyes and it won't harm you. But because they can be narrowly tuned to very specific frequencies in the mid-infrared where tens of thousands of different molecules will fluoresce, they can stimulate those molecules to fluoresce and produce a fluorescent fingerprint of their presence. So at a very long range, those lasers can be used to detect chemicals. The gases given off by wastewater, industrial processes, smokestacks, herbicides, pesticides, even some plant species. In addition, they can detect alcohol, fentanyl, and some of the aldehydes and esters that are given off by people who are suffering from diabetes and certain cancers. So the technology is very exciting, and it may be where we take this project next. Now, normally I would say, thank you very much for watching, please subscribe. But I'm going to make a little bit of a plea here. You may have noticed that some of the content creators that you follow have begun incorporating paid sponsorships into their videos. We have avoided that because we think that, number one, it seems to break up the flow of the videos and sometimes can come across as a little bit disingenuous. The point is, though, YouTube has progressively reduced the remuneration that it provides content creators for their work. And so I don't think that the motivation for this development is greed. I think it's survival. Since we began this channel about 10 or 12 years ago, we have never broken even financially from the revenue that we get from YouTube. What it has made it possible for us to continue is the generous support that we've received from our Patreon community, over 1,000 people that provide a little monthly support for the kind of expenses that are involved in the type of projects that we do. And in appreciation for that, we are going to begin releasing exclusive content to that community. Shorts, outtakes, bloopers, and as you can imagine with the kind of videos that we're doing here, the bloopers are pretty interesting and a lot of fun to watch. So if you think that you'd like to see us to continue these kinds of projects, these more aggressive and expensive projects, take a minute and consider possibly supporting us through the Patreon community. In any case, I want to thank everybody for watching, and I would ask you to please subscribe because it pushes the YouTube algorithm to distribute our videos to a much broader audience, get the message out. And in any case, I want to say thanks for watching, stay safe, and we'll see you soon.